Welcome to the session on iterative methods of solving simultaneous equations. The direct methods discussed so far involve many subtractions. When the terms involved in subtractions are nearly equal, their difference is nearly 0 and hence causes inaccuracies. The inaccuracies due to this inherent weakness of the direct methods cannot be completely avoided, whereas the iterative methods are free from such inaccuracies. When the coefficient matrix has more zeros, the iterative methods are more rapid than the direct methods. The disadvantages of the iterative methods is that it cannot be applied to all systems of equations. In order to give the solution of a system of equations, each equation of the system must contain one coefficient much larger in magnitude than the others in that equation, and the large coefficient must be that of a different unknown in each equation. In other words, after rearranging the equations if necessary, the large coefficients must be along the leading diagonal of the coefficient matrix. Among the iterative methods, we shall first discuss Jacobi's method and then Gauss-Seidel's method. First one is Jacobi's method. Consider the system a1x plus b1y plus c1z is equal to d1, a2x plus b2y plus c2z is equal to d2, and a3x plus b3y plus c3z is equal to d3. A system of three equations in three unknowns. If the coefficients a1, b2 and c3 are large as compared to the other coefficients, we can solve the system by Jacobi's method. From this system, we can write x is equal to, from this first equation, we can write x is equal to d1 minus 1 by a1 into d1 minus b1 by minus c1z. From the second equation, we can write y as y is equal to 1 by b2 into d2 minus a2x minus c2z, and from the third equation, we can write z is equal to 1 by c3 into d3 minus a3x minus b3y. Let us start with the initial values x naught, y naught, z naught. We put these values in the right hand side of these three. We will get the first approximate value of x as x1 is equal to 1 by a1 into d1 minus b1 y naught minus c1 z naught. From this, the first approximate value of y is y1 is equal to 1 by b2 into d2 minus a2x naught minus c2 z naught, and from this we will get z1 is equal to 1 by c3 into d3 minus A3 x naught minus B3 y naught. These are the first approximate values of the solution of the given system. Now, we will use these values in the same expressions for x, y, z and respectively. We will get the second approximate values of the solution of the system. That is, if we put x equal to x1, y equal to y1 and z equal to z1, in this we will get x2 is equal to in the second iteration we will get x2 is equal to 1 by a1 into d1 minus b1 y1 minus c1 z1, y2 is equal to 1 by b2 into d2 minus a2 x1 minus c2 z1, and z2 is equal to 1 by c3 into d3 minus a3 x1 minus b3 y1. These are the approximate values of the solution of the given system in the second iteration. Now, we will use these values in the expression for x, y and z. We will get the third approximate values of the given system and proceed this process till the difference between two consecutive approximations is negligibly small. We have an example. Solve the system 20x plus y minus 2z equal to 17, 3x plus 20y minus z equal to minus 18, and 2x minus 3y plus 20z is equal to 25. Here the coefficient of x is 20, which is the largest coefficient compared to the coefficients of y and z. In the second equation, coefficient of y is the largest, and the third equation, coefficient of z is the largest one. Therefore, we can apply the Jacobi's method. From the first equation, we can write x is equal to 1 by 20 into 17 minus y plus 2z. From the second equation, y is equal to 1 by 20 into minus 18 minus 3x plus z. And from the third equation, we can write z equal to 1 by 20 into 25 minus 2x plus 3y. We will take the initial approximations as x equal to x naught, that is x equal to 0. We will take the initial approximations as x equal to 0, y equal to 0 and z equal to 0. We will get the second approximation as x1 is equal to 1 by 20 into 17 minus 0 plus 0, that is equal to 17 minus 20. 17 minus 20 which is the first approximate value, that is 0.85, first approximation of x1. The first approximation of y is y1 is equal to 1 by 20 into minus 18, that is equal to 0.9, negative 0.9. And the third approximation is what z1 is equal to 1 by 20 into 25, that is equal to 1.25. These are the first approximate values of the required solution. In the second iteration, we will use these values in this expression. That is, this second approximate values are x2 is equal to, we will get x2 is equal to 1 by 20 into 17 minus y1 is negative 0.9, we will use these values. 17 minus 0.9 plus 2 into 1.25. y2 is equal to 1 by 20 into minus 18 minus 3 into 0.85 plus 1.25, and z2 is equal to 1 by 20 into 25 minus 2 into 0.85 plus 3 into minus 0.9. On simplification, we will get x2 as x2 equal to 1.02, y2 is equal to negative 0.965, and z2 is equal to 1.03. These are the second approximate values of the required solution of the given system. Substituting these values of x2, y2 and z2 in this expression, we will get the third approximations as x3 is equal to 1.00125. This is the third approximate value of x3. y3 is equal to negative 1.0015 and z3 is equal to 1.00325. These are the third approximate values. Continue this process. In the fifth iteration, we will get x5 as x5 is equal to 0.999966, y5 as y5 is equal to minus 1.0000778, and z5 is equal to 0.9999556. In the next iteration, we will get x6 as x6 is equal to 1.000, y6 as y6 is equal to minus 0.99997 and Z6 is equal to 0.99992. In the fifth iteration and sixth iteration, the differences are very negligible. Therefore, we can take the approximate solution of the given system as x is equal to 1, y is equal to minus 1 and z is equal to 1. This is the Jacobi's method. Now, we shall discuss another method, another iterative method, Gauss-Seidel method. Gauss-Seidel method. Consider the system a1x plus b1y plus c1z is equal to d1, a2x plus b2y plus c2z equal to d2 and a3x plus b3y plus c3z is equal to d3. From this system, we can write x is equal to 1 by a1 into d1 minus b1y minus c1z, y is equal to 1 by b2 into d2 minus a2x minus c2z, and z is equal to 1 by c3 into d3 minus a3x minus b3y. Here, we will take the initial approximations as x equal to x naught, y equal to y naught and z equal to z naught. Then, we will get the first approximations as x1 is equal to 1 by a1 into d1 minus b1 y naught minus c1 z naught. y1 is equal to 1 by b2 into d2 minus a2 x1. We will take the new value of x1 in this step minus c2 z naught, and z1 is equal to 1 by c3 into d3 minus a3 x1 minus b3 y1. This is the approximate values in the first iteration. Now, we will take these values to substitute in the right hand side of these expressions. We will get the second approximate values of x, y and z as x2 is equal to 1 by a1 into d1 minus b1 y1 minus c1 z1, y2 is equal to 1 by b2 into d2 minus a2 x2 minus c2 z1, and z2 is equal to 1 by c3 into d3 minus a3 x2 minus b3 y2, and so on. We will continue this procedure up to the desired accuracy obtained. But in the Jacobi's method, we will use the new approximations after getting all the values as new approximations. That is, after getting a set of new approximations, we will use in the next approximation. Now, we have an example. Solve the system 20x plus y minus 2z equal to 17, 3x plus 20y minus z is equal to minus 18, and 2x minus 3y plus 20z is equal to 25. From the first equation, we can write x as x is equal to 1 by 20 into 17 minus y plus 2z. From the second equation, y is equal to 1 by 20 into minus 18 minus 3x plus z, and from the third equation, z is equal to 1 by 20 into 25 minus 2x plus 3y. Let us take the initial approximations as x not equal to, y not equal to, z not equal to 0. We will get the first approximations as x1 is equal to 17 by 20, which is equal to 0.85. y1 is equal to 1 by 20 into minus 18 minus 3 into x1, x1 is 0.85 plus z naught is 0. Therefore, this is equal to, on simplification we will get minus 1.0275. z1 is equal to 1 by 20 into 25 minus 2 into x1, the latest value of x is 0.85, we will use that value, plus 3 into y1, y1 is minus 1.0275. On simplification, we will get z1 as z1 equal to 1.0109. These are the first approximate values of x1, x, y and z. In the second approximation, we will use these values on the right hand side of these three equations. We will get x2 as x2 equal to 1 by 20 into 17 minus y is y1, that is negative 1.0275 plus 2z, that is 2 into z is 1.0109, which is equal to 1.0025. y2 is equal to 1 by 20 into minus 18 minus 3 into x2, x2 is 1.0025 plus z, z is z1, that is 1.0109. On simplification, we will get y2 as y2 is equal to negative 0.9998. Then z2 is equal to 1 by 20 into 25 minus 2 into x, x is x2, that is 2 into 1.0025 plus 3 into y. latest value of y is minus 0.9998, which is equal to 0.9998. These are the approximate values in the second iteration. In the third iteration, we will get x3 as x3 is equal to minus 1.000, y3 is equal to minus 1.000, and z3 is equal to 1.000. Therefore, we can take the approximate values of the required solution as x3 equal to 1, y3 equal to minus 1, and z equal to 1. In this method, we used the latest values of unknowns in the next approximations. Note that the convergence criteria for the iterative methods is the iterative methods will converge if in each equation of the system the absolute value of the largest coefficient is greater than or equal to the sum of the absolute values of all the remaining coefficients. The greater than condition must be satisfied in at least one equation of the system also. Thank you for listening this session. Thank you all.